I am talking about ASIC heat reuse. A little bit of background on myself. I was a thermal engineer in the aerospace industry for about 2 years at United Launch Alliance down by IKEA. Spent a lot of time predicting heat rates and temperature and whatnot. And aerospace wasn't my calling. Went down the Bitcoin rabbit hole, and I left that role in January and said to myself, okay, I gotta learn more about heat from Bitcoin miners. There's a lot of it. People trying to get rid of it. What can we do to make it more useful and use that? So that's kind of my focus and my background, and I hope you guys like what I have to present here today. It's a little bit of my agenda. So overall, what is it? Some fundamentals on energy and heat transfer, quantity versus quality, some use cases, what I've broken down into what I think are the 3 thermal tiers of waste heat reuse for Bitcoin miners, some of the hardware associated with that, firmware and software, control, how you manage this heat, control it, the economic things to be cognizant of, and then some benefits. So what is ASIC waste heat, right? So Bitcoin miners use ASIC circuits. That is a physical circuit that is designed to do one operation, that is the SHA-256 hash. They've been this way for a while. That helps them be highly efficient, so they can compute a lot of these hashes for very little amounts of energy, the joules per terahash. And so they're guessing numbers. They're guessing for a low enough nonce to correctly guess the block and win the block. And so through that process, electric energy is converted into heat energy. And this happens with nearly 100% efficiency. And what that means is nothing's perfectly efficient, but for the case here, it basically is you're not losing energy to other forms of energy, like your hash boards aren't vibrating. There's not like large-scale kinetic energy or motion. They're not glowing, hopefully, and creating light energy or too much sound. You don't hear the transistors making sound energy. So all of that electric energy is converted into heat energy with nearly 100% efficiency. And then the heat reuse is just the implementation of heat transfer principles to integrate exhausted waste heat into useful applications. How can we use this heat for useful applications? And so my whole thesis is that heat is a product, not a problem. We have to get innovative and creative on how to build this out and use it in the best way possible. So for some fundamentals, some boring stuff here at the beginning. I think it's useful to know the laws of thermodynamics. So the first law is just that there's the conservation of energy. Energy can't be created nor destroyed. It can only be transferred into other forms, right? So all the energy here on Earth, most of it comes from a giant thermonuclear reactor in the sky called the sun that does fusion. That solar radiation makes its way to Earth, a solar flux, and then it's absorbed by plant life and goes through all these different processes and operations. You can use solar collectors to collect the solar energy directly. Plants are consumed by animals. Animals die and decompose. Carbon life forms are compressed, covered by soil for millions of years, and they eventually get turned into organic matter, oil, what I call the most organic battery, the Earth battery, oil, hydrocarbons, right? And then in the context of Bitcoin mining, conservation of energy, like if you have 1 megawatt of electric energy flowing into your Bitcoin miners, that means you have 1 megawatt of heat to dissipate. You got to reject it, and you have to reject it at the same rate that you're consuming it to be steady state. Otherwise, you would have what's called a transient system, where if you're not rejecting 1 megawatt, but you're consuming 1 megawatt, then you're heating up, right? That heat's not being rejected at a fast enough rate. So conservation of energy. The second law here is just that entropy always increases. Some of you might know this term. It's a fun term, entropy. What is entropy? You can think of it a bunch of different ways. It's a measure of disorder or randomness. I like to think of it as a directional nature to the universe. So this is what defines the fact that nothing can be 100% efficient. For an irreversible process, you're always going to have some entropy generation. So, a useful example here is when you mix like creamer into your coffee, imagine the amount of work it would take and energy to molecule by molecule separate that creamer back from that coffee and separate the two. It'd be impossible, right? So that's entropy generation. It's tending towards this lower energy state, this disorder or randomness. And then at the mega scale, right, the universe is expanding, it's cooling off, that's entropy generation. Why is that useful for Bitcoin mining, right? When you go from electric energy to heat energy, there's a lot of entropy generation. You lose a lot of useful work potential. So there's a lot of efficiency loss. Could I take 1 megawatt of heat energy and convert it back into 1 megawatt of electric energy? Thanks to the second law, I know the answer is no. I could convert some of it back probably, but not all of it. And then the third law is just absolute zero. 0 degrees Kelvin, the Kelvin temperature scale, is a measure of absolute zero. It's negative 459 degrees Fahrenheit. That is the temperature at which crystalline structures cease motion completely. And why this is useful to know is temperature is just a measure of kinetic motion at the molecular scale, so vibrations. And so the faster your molecules are vibrating, the higher temperature you're at. So if you're at absolute zero, you have no molecular motion, you can't get any colder. That is absolute zero. And then for heat transfer, how we manage heat, there's 3 ways to do so. There's convection, conduction, and radiation. Convection is heat transfer through a fluid, so a gas or a liquid, molecules and particles interacting, bumping into one another, transferring that kinetic energy, right, through a moving fluid, air cooling, liquid cooling, immersion, hydro. And then conduction is heat transfer through a solid. So these molecules are literally just butting up against one another and they're vibrating, and it diffuses through a system. If you had, a long pole and you heated one end, it would conduct through to the other end. And then radiation is a measure of heat transfer with no medium. So it doesn't need any fluid or solid to transfer heat energy. It's just electromagnetic waves. That ties back into the third law. Anything above absolute zero is radiating. All of your bodies are radiating. You can see it with infrared cameras. Everything radiates that's above absolute zero. That doesn't really play a big role in Bitcoin mining. The temperature difference and just the environment we live in on Earth, it doesn't play a big role. We also have a medium we live in. There's gas all around us, air all around us. We're connected to things, so it plays a larger role in space when you're in the void. Here I just wanted to touch on quantity versus quality. So this touches on the second law of thermodynamics, and it has to do with how useful energy is. So if we have 1 megawatt of heat from a Bitcoin mining machine or a site, you get 1 megawatt of electric power converted to 1 megawatt of heat. That quantity is conserved, but the quality is not. So quality is a measure of how useful energy is. Electric energy, or power, is very useful. It has a variety of applications. You can charge your phone. You can power my laptop here. The lights are on. You can power a speaker. You can mine Bitcoin, right? That's high quality. It's very versatile. Heat energy is much more limited in its applications. And what I mean here is to do work, it's much more limited. If you value the heat itself, there's value in that. You can use the heat to heat your environment, heat your home, heat your building. But if we wanted to use the heat to drive some cycle or some process, spin an engine, power lights with heat, how would you do that? It's low quality heat, which makes it very difficult. It's not very useful. And specifically in the context of Bitcoin mining, we have low grade heat, which really just means it's low temperature. Low grade is typically what's called under 100 degrees Celsius. That's because a lot of industrial processes require steam, and 100 degrees Celsius is the boiling point for many fluids around there. So we have fluids, air, and liquid from Bitcoin mining machines that are far below 100 degrees Celsius. It's very low grade. That makes it challenging to reuse in other cycles, right? So it's good for heating, not good for work. This big long tweet thread on the right, all I'm pointing out here, it's just a little quick math. If you had 50 degrees Celsius fluid from a Bitcoin mine and then 20 degrees Celsius ambient temperature, that's around 70 degrees, right? That's a 30 degrees Celsius delta T, your temperature difference. The delta T is directly correlated to how much of that heat energy can be useful to be turned back into electric energy. That's a term called exergy. It's kind of the inverse of entropy. It's a measurement of how useful or the capability to do useful work with an amount of energy. So if I had a system, a temperature, a hot Bitcoin miner, that heat, as it comes into equilibrium with its surroundings, there's a limit, a physical limit to how much work I could do, how much motion could I create, how much power, how much electric power could I regain from that heat energy. And so with the equation here, 30 degree delta T from a 1 megawatt Bitcoin mine, only 92.8 kilowatts, so 9.3% of that heat energy can be converted back into electric energy. And that's not even taking into account the inefficiencies from the system, the heat transfer process, some of your machinery, right? This is like a best case scenario, just looking at like what's called a second law efficiency analysis. So now we're kind of understanding the constraints of using heat for useful applications. Good for heat, hard to do things with it. So what are these use cases? On the left here, I've broken down some ways you can use the heat directly. And this is kind of where you're unconstrained from the low-grade nature. Luckily, we as human beings, we don't want really hot temperatures. We don't like to live in those climates. So things like homes, apartments, building zones, hydronic systems. So if you have radiative heat from hot water and a boiler in your home, pools, hot tubs, things of that nature, we're kind of in the sweet spot for those temperature ranges with Bitcoin miners. The exhaust heat, 40 to 60 degrees Celsius. Greenhouses, food drying, a lot of food drying for produce, things of that nature where they want to dry things slowly with a lower temperature. Car washes, I think that's a great example. You want hot water to, clean off all the debris off your car. That's an example of a consumer that uses heat in a higher duty cycle, right? Like, it doesn't matter if it's winter or summer, the car wash wants warm water, right? Concrete mixers, distilleries and breweries are a great example. A lot of those manufacturing operations, and then district heating. District heating is a big one as well. University campuses. I know that steam is used in Denver for district heating, some of the old infrastructure. So here it's like a symbiotic relationship with heat consumers and these machines that produce heat, right, while they compute logic. Then there's the using heat for work side of things. It's super fascinating. There's no proof of concepts yet in the Bitcoin mining sphere. The goal here is to drive a thermodynamic cycle with heat energy. That was what I described from the second law, exergy, entropy. How can I use this heat to convert it back into kinetic energy or electrical energy, some other forms, right? There's something called an organic Rankine cycle. A Rankine cycle just uses a working fluid that heat is put onto it, it vaporizes, and then that liquid becomes a gas, and it expands, and it goes through a turbine, and when it expands, it spins this turbine. And on the other end of that turbine, you have a generator, which is just the inverse of a motor. So if you put current in, you get motion. If you put motion in, you get current. So that's a way to turn heat into vaporization into motion. And the organic side here is just they choose a specific fluid such that it boils at the right temperature. It boils at a lower temperature. So you can actually create motion from low-grade heat like a Bitcoin miner. The challenge here is the overlap. Usually they want 70 to 80 degrees Celsius as the inlet temperature. And so that's a big one, right? Because that's kind of just above the upper bound of what Bitcoin miners exhaust in terms of liquid cooling from hydro or immersion systems. So it's like just in sight, right? And then related to that are absorption chillers. So an air conditioner is just a heat pump in reverse. You apply power to a compressor, it compresses a fluid, it goes through a thermodynamic cycle with condensers and evaporators. Anyways, you can create a cooling load from your refrigerator or your air conditioner by putting power in. In an absorption chiller, you put heat in, and it drives this refrigeration cycle such that you get a cooling load out. And similar to the organic Rankine cycle, it's like 70 to 80 degrees Celsius as the lower bound. So this is more of a question is like, I don't know exactly what our constraint is. Is there some fluid out there, a material science question, that has a lower boiling point that would solve all these problems? If so, why hasn't it existed yet? The HPC and AI side of things, I think they could also find value in this, right? But these are some use cases to use the waste heat from Bitcoin miners that I foresee as becoming near-term proof of concepts, quite possibly, to turn that heat energy back into some form of work. And I didn't really define work, apologies. Work is just force times distance. It's a measure of mechanical work, electrical work with voltage and a charge, or fluid work is pressure times volume, and then pressure is force over area, and volume is area times distance. So the areas cancel out. Force times distance is work. This is the fun stuff. So this is kind of what I've honed in on lately, the thermal tiers here. Knowing all that background, okay, how can we use waste heat from Bitcoin miners? There's the home miner side of things, under 100 kilowatts. That would be a really big home, or apartment building maybe. Home heating, space heating, pools, hot tubs, water tanks. The challenges here are the equipment is expensive. I mean, if you're buying a Bitcoin miner for heating infrastructure, it's quite an expensive piece of kit. Requires some infrastructure, possibly. Maybe if your home's already on a hydronic heating system, or you can, I know some plebs out there duct it into their central heating, HVAC, right? You can get nifty with it. But the uptime challenge is what I see as the problem with this one. So if you don't have competitive power pricing to be profitable, at the end of the day, Bitcoin mining for heat doesn't have to be profitable. It's a subsidy. The heat is the product, right? It's like a double spend to get the sats, right? It's just offsetting your costs. And that's awesome. But in the summer, you might not want the heat. So if it's not profitable to mine the Bitcoin, why would you do that, right? And so uptime is a big variable. It's a big knob here. You know, back to the car wash, like they use heat year round, so you get a better return on investment. If you're going to spend lots of money on expensive heating infrastructure, you want to be running it as often as possible. So that's something to consider for the home miner side of things. That's teeing off into the industrial operation side. So medium, 100 kilowatts to 1 megawatts is kind of how I've defined it. And here it's looking for symbiotic relationships with these long-term heat consumers. They use it in large quantities throughout the year. Warehouses, car washes, manufacturing operations, colder climates maybe. They're familiar with system modification. That was another thing I didn't talk about with the home miners. I mean, we as nerds and Bitcoiners, I'm down to tinker with the machine and strap it into my HVAC duct, right? But I'm not going to get my mom to do that, let alone like a random neighbor who's never heard me rant about Bitcoin, right? So there's a much better business case for these industrial operations, right? They're used to CapEx, return on investment, their finance deals, maybe there's some credits and subsidies you can get because, hey, why not play into that? You're going from a carbon-based heating where you're maybe burning natural gas or propane and now you have electric heat. Don't worry about where the electricity comes from. And then there's much more opportunities for these operations to have higher uptime. And then finally, there's the pubcos, the mega miners, and that's where I think about, you know, these using waste heat for work, right? They don't want the heat, these large mining operations, 1 megawatt plus. They want to reject it at the same rate that they're consuming power. Just get rid of it, right? We don't need it, we don't need it, we don't need it. But I think it's a honeypot opportunity. If someone was able to get an organic ranking cycle attached to a 10 megawatt facility, you know, it was 9.3% efficient, maybe cut that in half with some other losses by the cycle and pumping and heat transfer process. Say you installed the system and you cut their power bill by 5%. Okay, well that you just reused your heat to say that you buy 5% less power from the grid. That's pretty cool. I mean, ultimately, maybe you can get that same upgrade just by going to a newer gen machine. I don't know if it's really worth it. I'm really fascinated to see how that plays out. Same thing for absorption chillers. Maybe there's some way to provide a cooling load to your technicians or any other nearby facilities. Kind of a proximity constraint with these ones is too, right? Because these large mining sites tend to be in the middle of nowhere. They're not next to businesses or things like that. So I think as soon as this is cracked, everyone will take notice. It'll be really popular and innovative. It'll be very creative to implement something like this. But right now we have those temperatures that don't exactly overlap for these systems to work with Bitcoin miner waste heat. You know, one way you could add a little bit of waste heat to get the temperatures where you want them is off-grid, right? You have combustion then from natural gas. So you could take some of that heat off of a combustion process. That'll be most of your heat, honestly. And then just add a little bit more from your miners. Then you could drive that organic ranking cycle. Or solar collectors, I've heard that proposed. They're basically just, instead of solar panels that collect electric power, they just collect heat from the sun, solar generators. You could top off your heat from the Bitcoin miners with that as well. But solar is transient, it's intermittent, it's not steady state, so I don't know if there's some opportunity for a thermal battery there or something of that nature. It's food for thought. I'm really interested to see what plays out with the pubco side of things. My interest is the industrial operations. I think this is where we should really hammer home with the current state of the industry. The machines are industrial, they're expensive. I think this is the perfect target market for waste heat reuse for Bitcoin miners. I know there's guys on the home miner side of thing bringing like really nice, slick products to market, guys like Zach Bomsta at Unbound Networks and the Loki boards and things like that to make it really simple to just plug in a space heater. But I'm thinking more integrated systems, right, where you can turn your thermostat in your house and the system does what it needs. It's not just a space heater in the corner, which is, by the way, how I heat my apartment right now. So what kind of hardware is involved in managing this heat? How do you do it? I talked about how convection and conduction are the key methods for moving this heat around from Bitcoin miners. It's carefully managed via specialized infrastructure. So you have the mining hardware, and then you have heat transfer infrastructure, and then there's all the associated mining hardware that you need, 240 volt power, networking, power infrastructure, etc. So here is my space heater. That's my S9 there on the left. I installed 140 millimeter Noctua fans on the top of it. Shout out to Rick from Crypto Cloaks for some of that CAD stuff. And what does that do? That's a larger diameter fan, so it can spin slower to move the same amount of CFM, same amount of air. When it spins slower, it's quieter. So that's something that was really important for the air side of things. Anyone that's been around an air-cooled machine knows how loud they get. It was also downclocked to 400 watts, so it's very, very underclocked so that it's still not loud. Also 1400 watts. I blew a fuse in my old apartment. Then you see here in the middle an immersion machine. There are some immersion-specific miners out there from What's Miner, but you can also just submerge an air-cooled machine in immersion. So what's happening here is you take the fans off in that case, and you're still cooling via convection. You have a fluid still. The fluid is no longer gas. It's a dielectric oil. Dielectric means it is not electrically conductive, so it won't short circuit because the whole thing is submerged in the fluid. There's a lot of benefits to this. Some people are bearish on it. I think it's actually the sweet spot for heat reuse. If the whole machine is submerged in fluid, you get the heat off the power supply, you get the heat off the board, you get the heat off you get all the heat. The whole machine is submerged in fluid. It's also very heavy fluid. It's thick. It has what's called a high specific heat capacity. It's viscous. The specific heat capacity means it takes a lot of energy just to change the temperature of that fluid. So it's trying to pick up a heavy weight takes more energy, right? Same thing there, and it's conductive, so it has a higher conductivity than air. So these machines are silent, essentially. They run pumps, and you can overclock typically higher than air-cooled machines. And the benefit of that large amount of insulating fluid is it helps prevent against thermal shocks from expanding and cooling, heating up and cooling the control boards, the hash boards when you cycle the machines. That can damage your hardware over time. You don't want to cycle it too often. You want to ramp it down, not just kill power on, kill power on. So that kind of solves that problem. Immersion machines are highly resilient in that regard. And then you see hydro here on the right, which is much more specialized. It's a much more high-performing way of cooling just the areas you need to cool. So in this case, instead of all these fins and heat sinks that just add more surface area so you can reject that heat to convection, you have what's called a water block, and it's literally on top of all of the ASIC chips, and it has all these jets, and it's literally jetting fluid onto the chips. And this way you can use water, which is conductive if you don't demineralize it, but you get high convection coefficients because of the jetting, so just high velocity, you're throwing it at it. By the way, did you ever notice that if you sit in like a cold tub and you don't move, you get like this thermal boundary layer on your body, but if you move your arms, it's way colder? That's convection coefficient, right? Your heat transfer coefficient. So they're jetting it. It's like being in front of the jets on an ice bath, really cold. And here you don't have to cool all the other components. You also don't have to deal with the dielectric fluid, which can be expensive. It can be toxic in some manners. It's heavy, it's heavier. So a lot of people, there's conflicting opinions. Some people don't like immersion, some people do. There's trade-offs to each. In terms of heat transfer, both of them, the fluids are much better at transferring this energy over distances. That's because they have that high specific heat capacity, which means it takes more energy to change the temperature of it, right? You know, your air in the room, you got a heater, it will diffuse, right? It'll diffuse very quickly, and it's hard to get this heat if I was blowing hot air out of my mouth to the other side of the room there, but if I was blowing hot water to the other side of the room through a tube, it will carry that heat over much longer distances. Here's some of the other hardware involved. So in the top left here is a liquid-to-liquid heat exchanger. It's called a brazed plate heat exchanger. And then in this case, you would put maybe, so for the immersion system, for example, you have this expensive oil that you don't want plumbing all through your house in the case of a leak. So you have the machines that the heat is extracted from the machines to the oil. But then you run that through a brazed plate heat exchanger, and then on your other end of the heat exchanger, you just plug in your hot water loop from your hydronic heating, your radiant heat in your house, or your hot tub, or your pool. So two of those ends just go into whatever water you want to heat. The other two ends go into your oil, a little bath for your miners. Then in the middle, on the top middle, is just a hydronic manifold. So after we go through the heat exchanger, you could take some of that heat, and then you could take it to this manifold and send it to all the different rooms in your house, right? There's a pump here on the top right. That's just a hydronic heating pump, so you can send it throughout your house. And then back to the bottom left, that is just a hydronic radiator. So hot water flows through that, has a lot of fins. The fins get hot from the hot water through conduction. That convection transfers the heat to the tube, and then the tube conducts all that heat to all these fins, lots of surface areas. So then the air just flows over the fins, and it takes all that heat, puts it in the room. In the middle here, you see a larger infrastructure item. That's called a dry cooler. So this would be more for not reusing the heat, but rejecting the heat. So what this does, it's like the radiator, but it's just a bunch of tubes with many, many more fins and then fans on top that ramp up and down to force air through it. It's called forced convection. And that's how most Bitcoin miners right now, the large scale, they reject that heat. So back to that high uptime discussion, if we wanted to reuse the heat in the winter but reject it in the summer, how do I reject it? You need a big dry cooler outside to send that heat away when you don't want it. And if you kept it in air in the bottom right here, that's just your HVAC ducting. You could also do this way. This is kind of how a lot of plebs have done it, strap it into their house. And I also think it makes sense for warehouses, things of that nature. We don't have to transfer the heat over such large distances. And also when you get to large distances with fluids, with the liquids, the pumps can get very expensive. It's a large pressure head. You ever try to suck something out of a straw? The longer the straw, the harder it is. It's the same thing. So when you start pumping over thousands of feet, I mean, you need multi-$1,000 pumps to do that. What role does firmware and software play into heat reuse? So dynamic performance scaling is a big one here. I know Brains does it. I think LuxOS does it as well. It's where I can set a target temperature, and then the machine will kind of throttle, adjust voltages. Help me out here, David, if I'm messing something up. But it will optimally perform under that target temperature threshold. Yep. Another thing here that I thought was interesting was reward splits and payouts. So back to what I touched on for, say I got my grandmother to install a hydronic heating system. It would probably take me a long time to get her to manage a pool payout system, maybe even download an iPhone app. Right? So maybe someone like me would manage that for her, and then having accounts and sub-accounts where I can split those sats, convert them into dollars if your customer or client doesn't want sats. Maybe they're not Bitcoiners yet, pre-coiners, let's call them. That kind of paints the picture for maybe a distributed hash rate network where you and your small community can help reduce people's electric heating bill costs or utility heating bill costs, but they don't want the burden of trying to manage the hash rate, and you could do that. So I think a distributed hash rate management system would be valuable too. I don't know if this exists where I can kind of look at all these different sites and see that everything's running healthily. I don't know if that exists yet. API integration, stuff like that as well. So you can ultimately control this system by your thermostat. Yeah, so getting into control. It's all about, to pay off the machines, you want high uptime, but to be eligible for that, you need cheap enough power because you're going from maybe your natural gas heating bill to electric heating now. So it has to be competitive, and say it is competitive for you to heat with electricity and then also still profitably mine in the summer months. It's all about managing that heat, where it goes and when. That's reuse or reject, reuse or reject. Obviously temperature management, things like dynamic performance scaling for that. You want to make sure everything's running smoothly and at the right temperature. You're not overheating or frying anything, that would be bad. And then control of your HVAC and plumbing, all of this roping into some logic that connects to your thermostat. So here's a diagram I threw together for a hydronic heating system. I'll kind of just stand up here and point so everybody can see. This is your immersion or hydro rack with all your miners. That heat goes to the left through that first pump. That purple box up there is where you hit your first dual loop heat exchanger. That heat is transferred to the blue loop. So now the heat is in your water glycol system. You don't always need glycol. Glycol is an antifreeze. It's in your car radiator. If you're in a cold climate, you'd want glycol so the water literally doesn't freeze in the pipes when you're not running it. That transfers down to a manifold, and then off the manifold you can just tap off in different lines. Let's send it to all these different places. So the first tap off was to another cross-flow heat exchanger. Here I'm going from water to water. And the reason I'm doing that is I don't want the water glycol mix heat fluid going into the pool. I don't want glycol in my pool. So the pool system is closed. It's a closed circuit. And then the second cross-flow heat exchanger just transfers that heat from the water glycol hydronic loop to now my hot water tank, so I can shower with mining sats. I could heat my hot tub, my pool, things of that nature. The second one here is maybe a crawl space dry cooler. I was trying to pitch this to my parents because whenever I go home, I have to wear 4 layers of socks because the floor is so freaking cold. They don't have their crawl space insulated. I think that would be awesome. And then maybe some different zone heating, hydronic radiators. And also, you don't have to go liquid to liquid at the end of the day. You could just pump this into a dry cooler. You could take the fluid, say you want the immersion or the hydro rack because it's quiet. You don't want all the loud fans. You take that hot fluid, you take it to a dry cooler, which converts that hot fluid into hot air. And then you could just put HVAC ducting on top of the dry cooler and have an appropriate fan sizing, fan speeds to make sure you're getting the CFM you need. And that could distribute the heat in gas form around your environment. And then the control part of this is, okay, what if I didn't use all the heat? So it's cold out, but it's not cold enough for me to use all the heat, right? But I don't want the miners to overheat. So if I didn't use all the heat in this first heat exchanger, and I don't use it for all my zone, maybe it's 30 degrees out and I designed it for -10, then some of the heat is still going to go back to the miners. And if you have to cool it off to their desired inlet temperature or they'll overheat. So here you have an external dry cooler. And this is where you would take that heat and dump it outside, whatever you didn't use. It's about designing the system properly. There's a lot of pump sizing, radiator sizing, heat exchanger sizing. Make sure everything's optimally designed for your coldest day. Maybe it's overkill. Maybe the parts are 10 grand more to design it for your coldest day. So you say, screw it. We're not going to design it for the coldest day to save money. And maybe on that coldest day, you don't tear out your natural gas heating system and that picks up the slack. There's a variety of ways to do it. You can kind of split it up however you seem fit. All these off-the-shelf components, they all exist, and then you piece it all together. So how do the economics work? I've alluded to this a little bit. There's the CapEx, right? There's the mining hardware, new or used machines. I think that heat reuse is an excellent opportunity to reuse older machines because you're not so sensitive to the efficiency, right? The heat is a product in addition to the sats. It's a great way to reuse older miners. It's a great way to lower the CapEx by a machine that is 1 or 2 years old after it's heavily reduced in price. Then there's the heat reject and reuse infrastructure, what I just outlined on the slide before here. There's engineering design involved, unless you can do it yourself, which is totally doable. I'm trying to compile all the information for people like you guys to do this. And then maybe there's tax credits and subsidies as well. On the operating expense side of things, there's the offset heating cost. That's saving, maybe as natural gas or a propane tank if you're in a rural area where you don't have to truck in propane once a year. And then your power cost. By the way, in the case of electric heating, some people literally have electric boilers. What is an electric boiler? Here's an electric space heater right here. It's literally just flowing current through copper traces, and friction is happening at the atomic scale, and it's just causing those wires to heat up, and then they blow air over it. It's literally a computer that does no logic. That's all it is, right? So for anyone that has an electric boiler, come call me, because any Bitcoin miner you install will be cost saving to you, any. And then there's the baseline heating method. Yeah, so natural gas and propane are great. Natural gas is cheap in America. We didn't blow up our oil pipeline yet. So we have abundant natural gas, unlike Europe. So that makes it more appealing to rural areas where they have this propane or electric heating. And then what are the key variables that determine if this is a good fit for you, right? I mean, the incentives are aligned here if you meet all the criteria to save, right? If you can save $200-300 on your heating bill a month, maybe also mine profitably in the summer months. So it's the climate you're in, how cold is it? The duty cycle, how often do you use heat? That's where I think those industrial operations make a lot of sense. The scale. What I've highlighted here is revenue versus non-revenue generating assets. If you're going to buy a dry cooler and a pump, right? Only the Bitcoin miners produce sats, not all the other stuff. So if you buy a tank for maybe a 10 miner tank, that'd be overkill if you only have 3 ASICs in there, right? That's a non-revenue generating asset. So you got to make sure this is optimally designed, right? You want the most revenue generating assets to meet your target heat demand. Hash price is another big factor here. And that's hard to factor into things, especially when you're trying to convince a non-Bitcoiner. I promise it could be more, right? And then amortization and financing as well. There's a lot of upfront capital involved. If you were to try and make this a business where you wanted to sell methods of saving on heating bills to your community, I mean, you could have them front the cost for the hardware, and then maybe they get 90% of the sats. That's why I think the sat split is really important. Or maybe you upfront the capital, and they're like leasing miners, they're leasing heaters from you that pay them, and then maybe they get 20% reduction in their heating bill, but then you also get back some revenue. So there's infinite ways to build this out. So at the end here, what are the ultimate benefits? There's the utility bill saving. hopefully, right, if you're a good fit. Otherwise, you wouldn't do something like this. There's the physical decentralization of hash rate, which I think is good. I don't think it's as big of a threat as the digital decentralization of hash rate, right? So the block template construction. However, more physical decentralization to hash rate, more sites, more miners, it's more opportunity for the digital decentralization. All those individuals get to choose how they construct their block templates. If they want to go with a transparent protocol like a transparent ocean block template pool to see how those are constructed. And then a really big one is that I see is the widespread utility value of mining, right? And this one's a little bit harder to put a finger on. Bitcoin mining is vilified by many. We're all aware of that. If you can come into a community and say, or introduce it into their home or their business where they're saving money, they might not need to know how it works. It's a black box to them, but it's literally saving them maybe 30%. And in the summer, it's still paying them, right? There's a direct, tangible benefit to someone who might not know much about Bitcoin mining yet. And I think that's extremely valuable. So if someone comes in and says, hey, you shouldn't be doing this, they go, wait a second. You mean you're trying to take away that thing that saves me money? No, I like that thing. And then stability to mining economics. If we were able to make this work where you can get the heat reused into a work application for maybe the public miners or the large-scale mega miners or any mining sites that might be set up in a symbiotic relationship with a heat consumer. You know, we're transitioning from block rewards being mostly block subsidies, newly minted Bitcoin, to transaction fees, which are more volatile by definition. So this is just a nice like baseline. If you're selling your heat, it doesn't matter what the hash price is. It doesn't matter what the transaction fees are. It doesn't matter how busy the network is. You're selling the heat. It's just a revenue stream, an additional revenue stream. And if you looked at these sites where these systems are integrated from, you know, a 30,000-foot view, it's just increased total site efficiency. You're being more cognizant and mindful of your energy consumption, right? You're no longer buying power and heat. You're buying power and then reusing the power that's converted into heat. So you're a more efficient user, more conscientious. So that's my presentation. Are there any questions? Yeah.
Is anybody using Peltier modules to turn these into air conditioning units as well as a heater, so it actually can be useful during the summer?
I would love to see mining used for air conditioners. That would be that absorption chilling cycle. I haven't seen anyone build out a proof of concept or even really hone in on it lately. It's something that I need to explore more, but I'm unaware. Yeah, Sam.
Yeah, I gotta ask, what would be your best guess on what percentage of hash rate in, say, like 20 years will have some heat reuse component?
That's a great question. There's probably way smarter people in the crowd to answer that than me. Yeah, that's a good question. I don't know. I think that, well, I do know that 50% of energy consumption is used for heating purposes annually, which is a large market. What amount of that is for higher grade heat where the miners just don't fit into it at all? I don't know. And then just with the network hash rate increase, you know, 70% a year over year on average, what does that ultimately factor into? I'm not sure. I mean, one thing I would say, looking out 20 years, what does that mean? I think that we'll see less increase in total network hash rate year over year, which to me means the difficulty won't be increasing as fast. We're also going to see less large gaps in the efficiency from the ASICs just due to Moore's law too. So there's like a life cycle to these heaters too, right? They're eventually going to become obsolete. Maybe they're saving you. It's a heating system that pays you, but the amount it pays you goes down every year because of network difficulty, right? Maybe the price targets up fast enough that it doesn't matter, but eventually you might need to recycle the machine. So that gets me thinking about things like form factor, if they would just stop changing the size so I don't have to keep, you know, that's where immersion comes into play. It's really nice to just put a new thing in a bath. It doesn't matter if it changes size. I didn't really answer your question, I'm sorry, but I'm not sure. I'm riffing now.
Another additional benefit I thought of, and like, I don't know if you thought about this, is just like you can figure out like how much additional hash rate
Yeah.
could be online in 20 years, like that kind of helps the issue.
Yeah. I would encourage you to check out Zach Bombstone on Twitter. I think he had done some math on that, like 1 million homes with his little space heaters and how much hash rate that equates to. I don't know it off the top of my head.
River also has a report about like the pathway to 1 zettahash by Sam Wilder or something.
Yeah, it's my boss.
Okay. So you're just trying to get some free alpha.
That is a good report. Yep. I've been really narrowing in on these industrial operations, running some numbers and general modeling on what this may look like. You know, maybe it's $100,000 a megawatt for your immersion cooling infrastructure. That's really competitive if you're going to China. Maybe 1 to 300,000. Anyways, the point is, from my math, I've seen like around 2 year with conservative variables like hash price and things of that nature. In the back.
For your home miner, do you have a thermostat attached to that so it automatically turns off when it hits a certain?
I don't. I've seen someone put that together for the S9 and the Crypto Cloaks case. I have not integrated that though. No, I just turn it off and on.
And the other question is, like, what do you see as far as savings, or what do you get back in Bitcoin, I guess?
On my S9?
Yeah, like every month, like, you know, how much are you saving in energy?
Yeah, I have 13.4 cent per kilowatt hour power where I live in South Denver, and with my S9 at 400 watts, maybe it costs me like $1.40 a day, 24 hours to run, and it maybe mines me 25 cents. So 15 to 20%.
Like for someone who has baseboard heat,
Yeah,
like already electric heat,
right.
doesn't it make sense to just use
If they use electric heat, no matter which miner they pick, it will be better.
Yeah.
You could get, you know, a 5-year-old machine that is dirt cheap. Yeah,
Interesting. Okay. Thanks.
in the front here.
This might be a dumb question, but is there a reason they haven't built miners that produce higher heat so they can hit that?
I wrote an article about this, arguing for higher temperature chips. And I probably wrote it ignorantly because I don't know anything about chip design.
I know nothing.
Semiconductor physics.
Yeah, what I've learned from guys like Scott who developed the BitAxe, the Open Source Miners United group, when you get to smaller transistor sizing, nanometer processes, more efficient, right? Your distances are smaller between transistors. It takes less energy to move electric current around. You can run into leakage current, is that right, David? So you can get like errors at higher temperatures.
But basically, you can run into thermal runaway, and then the chip's gonna smoke.
Yeah. What was fascinating that Scott pointed me to, though, was like on some of the recent Antminer machines, they haven't posted their temperature limits on the newest ones, but on a few older ones like the S19, I mean, the chip is rated to like 110 degrees Celsius. It's the boards that are rated lower. The boards are rated to 80 degrees Celsius. I don't know if that's due to flux or solder. And I thought,
The chip temps operate higher, but yeah, every aspect of the whole electrical design has some kind of temperature rating.
right,
One example is S21 chips. It mains firmware will shut the whole machine down if a single chip hits 100 degrees C, and then it's off.
yep.
So that's kind of the limit on the new gen right now as we know it.
I thought I had this morning, Rob pointed me to some resources, was like, you know, if WhatsMiner is designing a machine for immersion from the ground up, they're thermally designing it. It's not meant to have gas as the convection. It's always meant to use this oil that is insulating. It's heavy, thick oil. Couldn't they maybe design it knowing that thermal cycling and expansion of the chips, because there's not as much of a temperature shock, and could that lead to higher temperatures? I don't know. I was looking through some of that documentation you sent me, but yeah.
There are high bandgap semiconductors that can operate at 300 degrees Celsius. And,
Oh.
The only thing is, I'm not sure what process nodes are supported at that level, like how large the transistors would be. So it's not quite clear how like competitive they would be from a hash standpoint, a hash rate standpoint, but they would produce high grade heat.
Yeah, the real challenge here too, to answer your question more, is economies of scale. You know, heat reuse from Bitcoin miners is very small compared to the marathons and riots and pubcos that are buying thousands and thousands of machines. So, I mean, it takes billions of dollars to develop a chip architecture from these companies, and why would they maybe put effort into designing something that is less efficient, right, but has a higher throttle temperature? Maybe doing some of the research that Sam suggested to see how big that potential market is could sway them in that direction. Or maybe it's like, what about binned chips or older processes that are a generation old? Could you still produce them and just rate them, integrate them into systems with higher temperatures? I don't know how it will play out. Yeah.
Yeah, my mind is used to cold environments and this like getting rid of the heat. Is there much hope for tropical regions of the earth with this sort of thing?
Oh, I don't know. I haven't thought too much. Just because it's a hot climate, you mean?
Yeah, so you're trying to get rid of all this heat. It's already hot. Is that just a fact of physics that it's not going to work well there? Or could you focus more on
Heat will always
the heat side of it?
Yeah, heat will always transfer if you have a temperature difference.
Okay.
So that's that second law, the directional nature always goes from hot to cold. So you'll always have heat transfer of some form. It becomes more challenging, like in a hotter climate like that or the Middle East. Like you have to oversize your cooling infrastructure. That dry cooler, which is what most large miners use to reject heat, it uses fins to increase surface area, so more air touches the hot stuff. And if it's a hotter climate, you need more area so that more air can touch the hot stuff, and that's how you can reject the heat. On the cooling side of things, it's really just about finding a fluid that can boil at a lower temperature or getting hotter chips. Yeah, Mark?
Well, related to your question, there's OTEC, where they're using engine or the
Geothermal.
temperature, and so it's actually only useful at the equator. So they take the difference between temperatures at low, deep in the ocean, and the ones that are up for that difference.
That's exactly how it
Using
works.
what you're talking about, and they're thinking that Bitcoin mining will actually be able to figure out how to go between the small scale that they've done and large scale. So we may end up with a lot of miners located around the equator because it's hot, and they'll be using the ocean to do it.
Yeah, that big temperature difference.
There's a couple articles that have been done. I forget the guy's name. If I think about it, I'll tell you. Yes, that's right. Thank you.
Not to mention that you don't even need the OTEC technology to make it work in the ocean.
Right.
You have a massive thermal mass. Just dump the heat in the ocean. If
Yep.
you're using liquid cooling anyway, you have a
It's a big sink,
Yeah.
big heat sink.
Boil the oceans, you mean?
Yeah, boil them. Dylan with the zingers. Yes.
If you're interested in mining privately, is this one of the best ways if you're on grid to hide your signature from the utility company? And I guess like more generally, have you thought through some of the privacy implications for mining this way?
Right, like are you suggesting maybe mining for heat in some symbiotic heat consumer scenario?
Heater,
Right.
Is the utility company going to be able to tell like that's a pretty weird space heater based off of your energy consumption?
Load management, that's what you call it. Yeah, I think you might be able to convince people of that. You get creative.
To comment on that, like I mine off my excess solar. So to the utility, they just see net zero. But my ISP will see that I'm calling home to my pool. So it is a way to track that.
Yeah, where you have some other form of generation. Yeah.
To get an idea of kind of the scale of like the miner build out that you need at different levels, like can you explain for that hydronic system what that would look like in terms of number of miners to make that work for I don't know, maybe like a 2,500 square foot home versus a small business, maybe a small brewery or something like that? What are you looking for?
Right. Yeah, it's a great question. I think a tool like that would be super useful. You know, if you're not familiar, I mean, you could go down to your boiler in your basement if you already had a hydronic system and it'll give you a BTU rating. And then you got to go online and Google how to convert that to wattage.
So I working at it with the hot liquor tank was like 500 barrels. Can't convert that to liters at the moment, but yeah, it's something that's that heat, that kind of heat storage container is always available.
When you have a large storage like that too, it's not a matter of how large it is to how many miners you need. It's a matter of how much heat that leaks. So if it's insulated, right? If it leaks 2,000 watts, that's joules per second, that's continuously. That means that one miner will eventually, that's 3,000 watts, one miner is adding 1,000 watts, it's leaking 2, but it's gaining 3. It'll eventually heat that thing up. It could take a week if it's 5,000 gallons. Thanks for listening, everybody. I do have 3 more slides that I wanted to go through. So I don't know if any of you have heard of this. We are starting a Bitcoin community hub here on the Rocky Mountain Front Range. It's called The Space. That was a temporary name. We stuck with it because it's so fun. Also, the space community is all here. Space Force, shout out, Colorado Springs. We are building a citadel, so we intend to have a physical building. We're exploring a real estate opportunity right now that is currently under contract. Planning to have some co-working spots, If you're a member, you can just come and hang out, shared space. We'll have amenities. We plan to have monthly events that are member exclusive. Additionally, we plan to have educational events that are more intended for the public. Right now in Denver, we have, Bitcoin and beer. It's really social, but it can be overwhelming if you're a newcomer to go there and learn something, and it's sometimes too social to even chat in the weeds about things. And then BitDevs, what we're at right now, often for me, it's like way over my head. I'm not a developer by nature. So it's good to have all these options, right? But we want to be able to offer a variety of different events. So be it Bitcoin for newcomers or Sovereign Health, where we have Jason Rick come talk about his ranch and eating well, and the Beef Initiative, or cypherpunks and privacy. We plan to have that all. So a working space, events, education, some amenities, resources, just building this physical community. I think look at everybody in this room. There's a really large and great Bitcoin community here in Colorado, and we want to build something together. So this is member run. It's not like we all just put a bunch of capital on the line and bought a building. We are currently building up our treasury right now so that we can build out all this infrastructure. We just got a server. I'm currently writing the website. This is not live. It's also not my forte, so it's taking me way longer and a lot of ChatGPT. But it's fun to learn. Things like that. Getting our Lightning liquidity, we're planning to have a mint, all these different things, right? A lot of infrastructure in the background. We've got our bylaws and charter. We're getting our member handbook drafted. We're in the process of filing our 1023 as a nonprofit right now as well. Dylan's in the room on the board, so is Joey, several of us here. And so we are accepting members right now as just founding members. It's $125 a month, and that is primarily as a donation to help us build this thing. It's literally ground up, right? So you are a founding member. We're having a monthly member event for these founding members, so we are doing something fun. But the real value here is to help us build this community and seek those rewards later on, low time preference type deal. We have a private Telegram group for our members. There's around 33 of us or so right now that are helping build this out. We have weekly meetings where we talk through all the committees. We've got real estate, marketing, business development. We signed one contract for a grant. We're maybe just about to sign another one that are some really awesome companies that are around the area that really see value in this Denver community. A lot of developers, a lot of educated individuals out here, a lot of Bitcoin companies as well. If you're a Bitcoin company and you want somewhere to work, we're planning to have some dedicated desks and office space. Maybe there's 2 or 3 of you guys out here and you want to just get your company in a place with other Bitcoiners. That's something we're planning to offer. So eventually here, there's those other tiers as well. We'll go to $150 a month just as a general member when the building's open, targeting like Q3, late Q3 of this year for that. And then we'll have add-on packages if you wanted a private desk or whatnot. So any questions on this?
Yeah, assuming that current real estate opportunity comes through, where's that located?
It's in North Rhino off the A line. Yep. Blake Station. Yeah. So here are donations, QRs for Denver BitDevs, and then the space as well if you just want to do a little donation to help us build this out. Very cool. That's all I got. We don't get kicked out of here like Catalyst, so if you guys want to mingle and chat or come talk to me or anyone else in the room, please do so. And if not, we'll see you next month.